Uh, uh, Hello, everyone. Welcome to the 128th Stanford MedAI Group Exchange session. This week, we have with us Ege Özsoy from Technical University of Munich to talk about his work on holistic OR domain modeling with large vision language models. Ege is currently a third-year PhD student at the Technical University of Munich in the chair of Computer-Aided Medical Procedures or CAMP. He completed both his bachelor's and master's degrees in computer science at TUM. Towards the end of his master's, he began focusing on holistic OR domain modeling at CAMP, and his research centers on achieving a comprehensive understanding and modeling of the entire operating room using semantic scene graphs and large vision language models. So, Eg, thank you so much for joining us today. And before you start, do you have any preferences on how you would like to take questions? Like, do you want people to interrupt you while you're talking, or you want to keep the questions till the end of the presentation?
No. Please feel free to interrupt me during the presentation. Of course, at the end, we will also have additional slot, but feel free to interrupt me.
Okay, great. So let's try to make this session as interactive as possible. And without further ado, let me hand it over to Ege. Okay.
So thank you for the introduction. And hi, I'm Ege. It's really nice to talk to you about holistic OR modeling with large vision language models. And because I realized that surgery overall hasn't been a talk that has been talked about here in this meeting a lot, I decided to not make this talk just about large vision language models, but kind of introduce the field a little bit, and from there move on slowly to holistic OR modeling, and then to our most recent works, which uses large vision language models. Good. So this is kind of will be kind of the content today. Just one slide to us, to CAMP. We are a chair at Munich. We have multiple locations. We're a really big group, 50 to 70 people, depending on how you count. And we have a group that is located in the university campus that really more focused on theoretical computer vision, deep learning general. And then we have three other locations at different hospitals. I am in this one called IFL. This is our biggest hospital location, where we focus on more application-oriented research, in my case, specifically surgery-related research. So that's just a very short introduction about our chair. And then the next topic is, what is surgical data science? So most of you have probably not heard of this. To explain that, I have to first explain a bit of the evolution of the surgery so far. Surgery in some form is quite an old thing, but in the past, it looked really almost like a butchery. It was very rudimentary. They were using very rudimentary tools, in some cases, not even anesthesia. So the ability to remove pain didn't exist. And of course, it was very bloody and messy, but it was relatively actually simple to perform. This thankfully already changed a lot. Right now we have surgeries that require surgeons with tons of training, that use many different equipment, different digital technologies at the same time, and they are supposed to consider the domain knowledge, the case knowledge, and the patient specific individual data all at the same time while doing the surgery. And this is why becoming a surgeon is one of the most time-consuming things. The training times are really out of control almost, and still they can make mistakes. It's really not an easy job. And even though all surgeons are getting a lot of training, we still see there are a lot of papers about this quality, or we see in the outcomes a significant difference depending on the technical skill level of the surgeon and the technical skill level of the staff. So still we know that the morbidity, mortality, any complications reduce a lot when the technical skill increases. And we see the future of surgery even more personalized, even more complicated in some regards, with a lot of things even being more interconnected, which will make it possible to treat even more illnesses, to get even better patient outcomes. But this increased complexity will even more add to the complexity of training and how much it takes, etc. And this is where we see the surgical data science playing a role. So essentially, surgical data science, what we understand is It's the data science with the goal of improving the quality of interventional healthcare by capturing different types of data. So it can be medical records, imaging, sensors, and I will talk about some of these during this presentation, and then processing, analyzing, and modeling this data with the goal of creating potentially smart systems that can predict certain events, that can predict clinical outcomes, assist physicians in decision-making, automatically control some devices, et cetera, et cetera. So this is kind of the field we are in, and kind of the ultimate goal is essentially, can we understand what is going on here? And most of you, I assume, are not familiar with surgeries. And even though I am, this is actually a very hard surgery to understand because this is an exceptional case. My point is the staff that is doing the surgery right now, they know exactly what's going on. But even if you took one of the more advanced large vision language models out there like ChatGPT and ask what is going on there, which I did, yeah, it just tells that there's some surgery going on. Maybe you can ask how many people it sees, but that's about it. It doesn't know anything about what is really going on in the surgery, what we are performing, which operation we are performing, which phase we are at, et cetera, et cetera. So it really has no clue. And when I say holistic OR understanding or modeling, I kind of use them interchangeably. What we mean is trying to use every single input modality, whatever, that is available to us in a modern operating room to enable decision support systems, context-aware intelligence systems, to allow automatic adaptation of certain systems to the surgery progress, and so on and so forth. So you really use everything we have to understand it as completely as possible, which would allow certain downstream tasks. And at the very end of the presentation, I will focus a bit more on the applications of this field. I said the goal is holistic OR domain modeling, but of course, there existed some line of research in this field before this was even something that you could dream of. And the earliest works actually also come from our chair way before my time, from 2006. And they started by analyzing tool data. So most of the tools in the surgery either already have an electronic signal. This can be simply a suction device that's turned on or off, or can be modified to provide this information. And this data is good because it's low dimensional, so you can handle this. You can write rules on this without needing deep learning. Again, 2006, we didn't have deep learning, and it's easy to interpret. And I would consider one of the seminal works, one of the pioneer works in this area was from Ahmad Ahmadi in 2006, where a bunch of surgeries were recorded, where a lot of the tools were providing some electrical information. Some of them were simply binary, being turned on or off. Some of them were actually even in degrees, how much power it was using, etc. And with this data, they were able to do the following. I will just skip in the middle. Essentially, they were able to compare two surgeries using dynamic time warping. Maybe you have heard of it. It's a technique to align two sequences that are same in order, but different in length in their steps. And you can align them. And what they could do is, first of all, they could compare expert level surgeon to an amateur surgeon, see how they are performing each steps, and also could see that if one video was essentially waiting for the other, that was an indicator that, one performed that step significantly faster. There was some additional follow-up work. I won't go too much into detail here, that added some hidden Markov models on top of it, and actually even recorded some external OR recordings. By the way, I hope nobody is disgusted by this. I am looking so much into these footages that I got used to it, but I realize it might not be very easy for everyone to handle. And you see huge core markers in the backs of the people here. So back then, tracking was done mainly using these huge tracking markers, but they were able to actually have a model that was predicting the current phase, the next phase, using, of course, not mainly the images, but the tool signals, as I said before. However, this kind of got much improved with the advent of deep learning in 2015 or 16, I would say. We were finally able to analyze video recordings, and this first became popular with laparoscopic recordings. Laparoscopy, for those that don't know, is a type of operation where you don't fully open up a patient, but introduce a camera through a hole and other tools through other holes. And this is called a minimally invasive operation, allows you to really keep most of the skin of the patient intact, leading to much better healing after and much less scarring. And because you already have a camera that has to be there for you to perform the surgery, these types of recordings were readily available, so to say. And these recordings provide very detailed information about the state of the patient, state of the tissue, and the surgical actions. And there were multiple data sets released on that. And the first works really focus on simply understanding the phase of the surgery. You see two data sets here. One has, I think, 7, one has 8 phases. And people proposed different architectures. This was one of the simpler ones, very similar to AlexNet, actually, if you're familiar with that. Just takes an image and outputs a label saying this is this phase. Of course, just looking at one frame wasn't very good in this. So there were approaches that suggested, let's use an LSTM to view the video in a temporal wave. Then there was another follow-up work from us again, which focused on using what is called temporal convolutions to better analyze this. And there was a follow-up work which used transformers to better analyze this. But the point here, these works were still only focusing on surgical phase recognition, which is a relatively simple concept. It just divides the surgery into 5 to 10 segments. This is still not something I would consider a holistic understanding, but these were the first initial steps. One of the more fundamental works in this area that started moving a bit in that direction is a work from Chinedu from Strasbourg called Recognition of Instruments, Tissue Interactions in Endoscopic Videos via Action Triplets, where they introduced this concept called action triplets. And just a teaser, I will talk about scene graphs very soon. They will have a lot of similarities. The idea here was that instead of just detecting a phase, now we want to detect all the instruments that are in the scene, all the tissues they're interacting with, and how they're interacting. So this can be like hook dissecting cystic duct, grasper retracting the gallbladder. And this is a much more challenging task, and there have been a lot of progress here already. And I will just show a quick video of how their method was performing and what kind of output they are getting from this. Of course, the disadvantage here is, again, we are only focusing on the endoscopic view. So even though we are understanding the endoscopic view relatively well, it's still only a part of the picture. There are many other signals we can use, and the next ones, a couple of them are some things we are considering to use more in the future. The community is looking into them, but have not been really explored so far. And one of them is audio. Be careful now. I hope some audio will play. I don't know if you're hearing. So even without seeing the video, and even though you're not particularly trained with these noises that are surgical, you can get a guess that this sounds like drilling. And that's something we've noticed, that of course you can understand which tool is getting used very easily just from the audio, but also detecting the exact point the tool starts getting used, like the exact millisecond, is much more easier from the audio than just the video content. That's one advantage. And I have one more example. Again, it was quite easy to understand that it is hammering, and not only that, but to understand the exact second the hammer hits the knee. This is one aspect where audio can be useful, and the second aspect is, of course, you can hear what the people are talking about, and you can hear what they're intending to do next. So in video, you only see what's going on right now, but in audio, potentially you could hear what will happen in the next 10, 15, 30 seconds. So that's one modality that we find very interesting. One of the more interesting modalities, which is also very challenging in terms of the data point, is using patient data. So right now, even most surgeons, I would say, are not considering the patient holistically while operating on them. They approach it more like, okay, this is a patient, I'm going to perform a knee surgery, I'm going to perform a laparoscopic something surgery. They don't really view all the attributes of a patient to decide how to best treat that patient, because this is simply very hard to determine and also very hard to teach. But ideally, in the future, we would want a system that considers everything about the patient. Certain imagings we have done, like CT or X-ray scans, certain diseases the patient have, which medication they are using, their exact size, shape, weight, and age, while making a decision. This is very hard to do research on because simply this data is lacking, but I think this will be very relevant in the future. Right now, just one example I can show here is in these kind of robotic knee replacement surgeries, you already have a CT scan of the patient's knee, and that's actually used directly during the surgery to guide the surgeons. So it would totally make sense to, of course, also use that data while as an input to this holistic understanding model. And finally, we have some anesthesia information which we could use. The anesthetist or the anesthetist team is responsible for tracking certain vital signs of the patient, monitoring the drug intake of the patient. And this is, again, a source that has not been utilized so far, and that would be interesting. Which brings us to the thing I will talk most about, which is the external RGB-D video recordings that are needed to really complete the puzzle. Without these recordings, we don't believe that a holistic OR domain modeling will ever be possible. You simply have to observe the operating room as humans would observe with simple cameras to be able to judge what's going on there correctly. And to explain this better, I have to first introduce scene graphs. I assume most of the audience is only vaguely, if at all, familiar with scene graph. Scene graphs.
Can I interrupt you to ask a question here about your last slide? So when you talk about, surgical room video, usually the point of view is fixed. The camera is fixed, like in generally all ORs, or like you would expect like different viewpoints as well.
So I think, and I will talk just briefly about that, but I think the more important point here is we have to observe the operating room outside the body, that's for sure. But how we do it, that can depend. There are some operating rooms that are installing fixed cameras onto the ceiling, always with the same location. There are some companies looking into actually adding cameras to their robots, and the robot moves, so of course the camera would be moving. Ideally, we wouldn't want to be a very fixed system in the sense that, oh, you have to build your operating room based on this blueprint, otherwise nothing works. That would really not be a scalable system. But how exactly this is observed, there are some ideas of using something like Apple Vision Pro or any kind of HMDs to also be observing the scene, or a combination of these. So I think that's relatively flexible.
Oh, thank you.
I was saying scene graphs are actually quite an old thing. They have been used a lot in computer graphics. Pixar even had their own universal scene description based on scene graphs. And the problem here is, how do you come, or what they were doing is coming from scene graphs to scenes. So the forward problem, as we refer. They were designing a scene and how it was supposed to look like in a form of some kind of a scene graph, where they were saying, here are my entities, here are how they're interacting with each other. And then semi-automatically, so either computer assisted or just their animators were bringing them to life. And I have a short video to show why we believe this is interesting for us. some of you might have seen this already. It is quite well known that many cartoons, Pixar included, are reusing their animations, just retexturing them. And while we don't know for a fact that all of them were created using scene graphs, we like to think that it's essentially as if you have the same scene graph, but just apply a different texture on top of it. So the semantics stay the same. And this is actually very, very relevant for us as well, because in the operating room, it's very, very similar. You might have a different looking operating rooms, different looking people, but essentially what's going on there stays the same. So we would like to work with a representation that is invariant to these changes that are not very important for our understanding. Of course, they kind of, the forward problem is kind of easy. When you already are starting with scene graphs, you can just generate different looking views from it. We have kind of the opposite problem. So we have to first, from surgical recordings, actually get to these scene graphs. Sorry, I will just take a short water break. So this kind of brings us to 4D OR, which was one of the first works in this area presented at MedAI 2022, where for the first time semantic scene graphs were used for OR domain modeling. And just for you to understand, like, this is a domain where there is essentially no public data available. So this research included first creating a set of surgeries, simulated surgeries, that like 10 of these, which then needed to be completely annotated with human poses, object poses, scene graphs, clinical roles, all of this. But the advantages, we could release it, and we did release this data, has been public for now, I think 3-4 years at this point, have been used quite a bit. It has both 6 RGB views, all of them also come with depth, which means we can actually generate a full 4D point cloud or a point cloud sequence out of it. And most importantly, for our purposes, we have these scene graphs. These scene graphs are kind of simplified a bit for clarity. Some relations are just left out, but the point is you summarize a scene by the entities you have, such as humans, different instruments, operating table, and their predicates. So this human is lying on operating table, so it's the patient. This other human is drinking into the knee of the first human, and finally the third human is assisting this first human, or the second human. And a second example kind of illustrates the point of the scene graphs, or what we are aiming for even better. This kind of disconnected component of this human touching this table is something you could consider almost irrelevant for understanding what's going on in the surgery. But we actually want to be agnostic to the downstream task that you might have in mind. So indeed, while this might be irrelevant for something like face recognition, it would be very relevant if you wanted to detect some sterility breaches. So we don't want to make a lot of very strong assumptions at this point about what is relevant and what's not. We kind of assume that the colors of the people don't matter and some things like that, but most things we actually want to capture and summarize in this representation. And once we had these labels, these annotations, we could build an architecture. And this was the first architecture. Back then, large language models pretty much didn't exist. This is 2021, 22. So our architecture had a lot of different components, but very simply put, it consisted of 3 parts. The first part was 3D human pose prediction. We used an off-the-shelf method, which we needed to fine-tune on our data set to be able to detect where all the humans are in the scene. And very similarly, we also trained a 3D object detection model to detect where the location of the objects are in the scene. And with these components, you essentially have all the entities, so all the nodes of your scene graph. Now, the only part is connecting them correctly with the correct relationships. And this was done using essentially, like you can imagine, you do a pairwise classification between the subject node, object node, ask a multi-layer perceptron by giving their point cloud embeddings, which predicate connects them. One predicate option is no connection, and the others, some examples you see here, like lying on, drilling, holding. So it's essentially you are just doing a pairwise classification over all the possible entities in your scene graph. And once you have done that, you end up with a scene graph that looks like this. And what we have then shown in this work actually is you can kind of forget everything that comes before the scene graph and only look at the scene graph or a bunch of scene graphs, a sequence of scene graphs, and solve tasks like role prediction, understanding the role of that person. As you can see here, it says human 0. You can now understand that it's a patient. You can do phase prediction, again, just solely based on the scene graphs. Actually, in most cases, it's simply rule-based, kind of proving the point that this representation is very powerful enough on its own that you don't need to refer back to the original images, original video recordings to solve a lot of the downstream tasks that you might be interested in.
I have a question for
Please
the
should.
yeah. So question for the instance level computation.
Mhm.
So in that phase, so is there any is there any task? Is there anything that for making pair the detected instance and then predicted in the human pose? Is there anything that making pair for both the detected object and the human pose? Is there anything?
So
Yeah.
So let me like this. Very hard to understand what this exactly does just from this slide, but essentially what we wanted to do is we wanted to assign every point in the point cloud to an entity because that will be needed in the next step. And 3D human pose prediction just gives you 10 or 14 joints of humans. 3D object detection gives you a bounding box over an object. This in both cases, we needed to project it and just based on some simple radius calculation, decide which points actually are belonging to that human. This doesn't have to be super, super accurate, but it has to be good for the next step to work, because in the next step, once you have these point segmentations, almost to put it that way, you now will take two of them and bring them together and ask a model, okay, given these 2 point clouds, how are they connected? I think that might be answering part of your question. Let me know if it's not fully answered.
Yeah, exactly. So I was wondering how you can making pair between the detected, the human, and the pose of the human, the surgeons. So yeah, thank you.
Yeah, so the pair, essentially, it is that in this work, it's not a very scalable strategy. You assume everything can be a pair. So if you have 10 objects, you have 10 times 9 different pairs that you have to look at, and most of them actually don't have a relation. So your multi-layer perceptron or whatever will just tell you no, 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 lying on, no, 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 drilling, no, 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 etc. So you just iterate over all of them, and that part takes care of deciding what is actually a pair and what's not.
Yeah, I'll ask. Yeah.
Oh, so go ahead, G.
Oh yeah. Real quick question. So did you use the YOLO basis detection model or mascars, something like that?
This is 3D detection. Just so back then, maybe you are familiar with WOTNet. I was almost going to use WOTNet, then a new method popped out of nowhere called group-free 3D detection, and I ended up using that. So this detection is in 3D. You could use YOLO if you were doing 2D, but then you would need to project it somehow back to 3D.
Okay, I see. Yeah, thank you.
I think one more question. So it looks like the vocabulary sets are fixed, right? How many humans you would expect. And again, I can see some of the instrument and operating table. So this is coming from domain knowledge that, okay,
Yes.
it's a knee replacement surgery. So you would expect, I don't know how many surgeons, patient would be one patient, but then how many instruments you would be expecting. So is this all coming like predetermined based on domain knowledge?
Yes, and it is, while it's not a huge weakness, it is a weakness that we actually will be addressing using large vision language models. But in this work, we essentially kind of overfitted our architecture, or overfitted or designed, however you want to put it, on the task we knew we had in our hands. But indeed, there were these limitations you mentioned. It is not a fully open world scenario ever. So surgery is not something like natural images where anything might happen. You can assume a lot of things, but I think overall there are some strong assumptions here that don't hold true always, but I will come to those.
Yep, thank you.
That's not important. So a quick follow-up work we did on top of this is called Labrador, where we introduced this concept called memory scene graphs. So essentially, so far, scene graphs have always been about an output. We were analyzing the scene and outputting this as a result. We wanted to see, the motivation was kind of like this. We have these 4D point clouds that are, 3D point clouds, sorry, that are very hard to process anyway. And now we want ideally a method that can do temporal reasoning, that can consider all the past 10 minutes, 20 minutes, 30 minutes of a surgery while understanding it. And we quickly realized that this is not a very scalable thing to do if you have to look at all the point clouds at once, all the thousands of them. So what we realized is, also during this talk, I have been arguing that scene graphs are a good summary of what is going on in the scene. So why not, in addition to using the visual input only from that single time point as before, use the scene graphs you have predicted so far as an additional input. So we are not actually viewing the temporal sequence in terms of videos. We are just seeing what we have predicted so far as a reference. And this was relatively straightforward to do. We essentially, every time we predict the scene graph, we add it to our memory. Then we have the, I think, yeah. We simply encode each scene graph individually. This is done with a graph transformer architecture. And then once you have these individual encodings, you use a memory encoder, in this case, an actually classic vanilla transformer that is able to give you a memory representation, kind of a high-level summary of what has happened so far in the surgery. And this was actually very beneficial because without a lot of overhead in terms of computation, this really dramatically improves the result. So V here is visual only, and M is memory augmented, let's say. And this is a consecutive sequence of frames from the recordings. And what we observe here is a visual only model was really confusing the suturing with sometimes cleaning, sometimes touching, because it's really hard to understand actually. And it doesn't know, like you do right now, that it is actually sequential. But with a memory augmented model, it was simply able to understand, okay, we have been suturing in the previous 3 frames. It's very likely that we will keep suturing. So this would be an example of a short-term reasoning, but also long-term reasoning, because the model already knows we have completed the surgery already. So we are clearly not going to be sterilizing the patient and cutting the knee. That doesn't make sense. It makes much more sense that we are actually suturing and closing the bone right now. And we indeed could observe in the attention of this architecture where it was looking, and it was essentially trying to understand which key steps have been completed so far, and this was leading to much better outcomes. But we had this problem that you actually already kind of alluded at, which is all of the methods that I've described so far fail to adapt to any new concepts that you might suddenly encounter that were not in your training set. And this can be something like suddenly observing a robotic surgery where there's this robot on the operating room doing the sewing, or even something much more simple as the drill, which was always orange during the training, is suddenly a totally different looking metallic drill, which is gray. And none of the models that I showed would have any chance of dealing with these. And this is now 2024, so we clearly saw that large vision language models had a lot of ability to a lot of word knowledge, and we felt that they might be able to provide us with something that wasn't possible before, which is the ability to use knowledge in inference time to guide them for better understanding. As the goal essentially was to build a scalable, adaptable, and robust system, which I believe has a chance to actually be adopted in the operating rooms. I'm not saying this model will, but the architecture and the things we are proposing actually has a chance of being used more widespread. And the first idea here was just, let's see how existing large vision language models are performing in the operating rooms. And we had some good and bad experiences. So LLMs have a good level of understanding of surgical concepts and phases. You can ask what are the key steps of a knee surgery. It can tell you. They are able to integrate multiple sources of information for holistic reasoning. You can tell something about the patient, something about the operation, and have it reason with all of these. And they can have a flexible output. They can output a scene graph. They can output a free text caption. While these are nice, we had two main difficulties. The first is they are not familiar with the exact steps and annotations that are present in our data set. So they don't know what is what. They don't know that this is solving. They have never seen scene graphs or anything like this. That was the first problem. And the second problem, which was even more significant, was while the language part of these things worked well, the vision part is really unfamiliar with the operating room. We kind of believe that some surgical text might be in the pre-training data, but surgical recordings were pretty much not in the vision training data, which means if you just input this image, this was Lava, maybe you have heard of this, one of the open source vision language models, and prompt it with something like describe this image using a scene graph, and I then even provided the list of entities it should use and the list of predicates it should use, and told it should output it as a list of triplets. And well, it kind of looks good, but actually it's completely nonsense. It predicts something like head surgeon cutting the instrument table, which is just not true. Assistant surgeon suturing patient, also not true. Actually, except the first one, I would argue all are just wrong in this data set. So while it kind of looks plausible, we kind of know LLMs are good at producing plausible content, it wasn't actually working well for us. So we had to, we still wanted to have a design that was very simple. We just wanted to provide a bunch of images of the camera angles, give it to the model, give it some additional knowledge as guidance. And this can be in form of temporal guidance, like with surgery graphs that I just presented in Labrador. So we want to include some temporal context just by saying what has happened so far. And we want to be able to include some information about the tools or predicates or the entities we now have in the scene that are unfamiliar to this model. And we ideally want this language model to skip all this human prediction, detection, etc., and end-to-end directly go to a scene graph representation. So the challenges were the following. The first one was how to adapt to the operating room. We quickly noticed that fine-tuning on our data set using the scene graph annotations was absolutely necessary. We opted for using LoRa fine-tuning because it was more efficient. We could do it only on one GPU. We didn't need to fine-tune the whole model. For those that don't know, LoRa stands for low rank adaptation. It's a parameter-efficient way of fine-tuning these models without needing to modify all the weights. And we also noticed that all the literature always mentions that you don't actually fine-tune the clip encoder, so the image encoder, you don't need to fine-tune. We noticed that this actually does not work for us at all. I think the operating room understanding of these image encoders are already not good enough so that you can just leave them as is. So what we noticed is that those also needed to be fine-tuned. The second challenge was we have in our data set 6 images, and we definitely want to be able to work with multi-view input. And to my knowledge, at least back then, none of the LVLMs were natively supporting more than one image. This was a challenge. We had some ideas how to deal with this. The first one, maybe the most obvious one is, well, let's just concatenate the image embedding. So if one image is 576 tokens, you have 6 of them, you're at 3,000 tokens. The problem is this is not very flexible to image count. Now suddenly your sequence length is changing based on how many images you have, which means the knowledge guidance comes at a different point in the sequence, the instructions come at a different point. This is confusing, and most importantly, attention is a quadratic operation, so we don't want to necessarily just increase the length of our sequence by 6 times because that increases computational costs extremely high. That would make it actually impossible for us to train these models. And the second idea was to use maybe something very simple like averaging the image embeddings. So you could take all the 6 embeddings and average them. The problem here is this would have been lossy regardless, but in this case, the embeddings of these images are actually spatial embeddings. So you can kind of imagine that the 576, I think it's like 19 by 90 or 20 by 20 or something like that. Essentially, it's a spatial representation. So when you now say, okay, we are going to average all the 6 embeddings, yeah, well, you're averaging the one patch which corresponds to something completely different in one image with another patch from another image. They have no spatial correlation, so just simply averaging them didn't make sense. And we did some experiments here as well. It wasn't working at all. So what we settled on was, for us, the most elegant solution, which is to introduce a learnable image pooler that is able to take as an input multiple image embeddings, 576 times n, and n is flexible even during training and inference, and converts it into one image size embedding. So always 576. And this is done using a small transformer architecture, trained end-to-end with everything else. And actually during training, what we do is we randomly select which views we want to use this time, and we shuffle the order. So sometimes you only have access to the third view, sometimes you see all the views, sometimes you see them in a different order. And that again goes back to the point that you were making, Amara. We ideally want these models to be able to automatically adapt to different view configurations without completely failing and not overfitting on these things. And I have some experiments to show that this model at least inhibits some of these behaviors. So it looks promising in that direction. One of the final challenges. Yeah, sure. Sorry.
Sorry to interrupt you. I have a question about the image pooler. So for learning the image pooler, like, do you use the same objective or is it different?
So essentially, it's completely end-to-end trained without any other loss or anything else. So as this kind of architecture, like this is classic language modeling loss that forces it to predict this output correctly. That is what is supervising the image encoder as well. There is not additional signal because we simply don't have any additional signal. We don't have a way of judging how the image pooler should behave, except for the fact that the language model should be performing good at the end of the day.
Okay, got it. Yeah, thank you.
But if you have that in your use case, I think it might be beneficial to add it as an additional loss. We didn't have it, so.
Okay, yeah.
And the final challenge here was how to represent scene graphs as a sequence. They are, by definition, graphs, so you have nodes and edges. From previous works, we already knew that encoding them as a list of triplets is a completely lossless representation. So you can just say head surgeon, comma patient, comma suturing, and so on and so forth, and this works well. The thing we needed to decide on was, do we extend the vocabulary of the large language model so that it can properly deal with these entities? Do we let it natively work on just the string and tokenize it however it wants? Or do we switch to a symbolic representation with letters and Greek letters that looks like gibberish to you right now, like A, B, beta? And I will talk about that later, why that is useful. The first idea was, let's just extend the vocabulary, but what we noticed here is, while this makes it much easier to parse the input and the output, because every entity is now one token, this essentially does not utilize the intrinsic knowledge of the LLM at all. So by design, LLMs might know that patient lying on operating table is a much more likely thing than patient lying on head surgeon. But when you assign them a completely new token ID, there is no existing knowledge they can use. They just have like 3000 and 3001, and the model doesn't have any understanding about what is more likely than the other one. So we quickly ruled this idea out. We didn't want to lose this knowledge that they already had, and decided to first follow this idea, which is also the simplest idea. Just let the LLM tokenize the text, which meant that each entity and predicate can have multiple tokens. Led to some parsing difficulty, but was nothing that you couldn't overcome. And this allowed us to use the intrinsic knowledge of the LLM. The problem here, and we are still using this technique for a lot of things in our work, but the problem here is the model really overfits to a lot of the concepts during training. As an example, in our data set, head surgeon never assists the assistant surgeon. It's always the other way around. And also, because the saw is always green and drill is always red, the knowledge guidance becomes useless. So you telling the model it's a green saw doesn't help at all, because it knows the saw will be always green in this data set. It doesn't need to pay attention to that. So we propose this third representation, which admittedly is the most confusing one, but it really served us very well and has a purpose. You automatically convert each training sample into an encoded representation. But what we do here is we replace each entity with a random letter, like A, B, C, D, and replace each predicate with a random Greek letter, alpha, beta, gamma, etc. And then you can represent your scene graph, as I had alluded to before, as a bunch of these letters and Greek letters combined. The key idea here is, again, because this is a completely random assignment, the model has no way of knowing that A should be connected to B with beta. It doesn't, these letters by themselves don't mean anything. So what you do then is you provide a definition table in the prompt explaining what each letter stands for, forcing the model to attend to these descriptions that you're giving to avoid overfitting on concept names, avoid overfitting on what is happening in data set, and allowing adaptability using textual prompts. So one example here would be, you can say, this epsilon is apparently a predicate, means use of a tool which is white, small, straight, plastic, and it's a surgical scalpel. And with this now, the model has to keep essentially referencing back these descriptions, allowing you to then change these descriptions in inference time and getting different results. So if you know your scalpel is now not white but red, you can just let it know just in inference time, just change the prompt, and it can adapt to that. Very similarly, we support also visual prompting. So instead of these textual features like white, big, small, plastic, you can just put one image per entity or per predicate, one example, and use its clip feature to summarize that image and use that as an adaptation method. So this, maybe you can view it as one shot versus zero shot, which was the previous one, but essentially just one example is enough to adapt to these new concepts. If there are no questions, I will present the last component that was necessary to make this work. So actually, I believe that what I presented so far would have worked if our data set was a bit more variable. We really have a very limited amount of variability in our data set. So even if you go back to this example, the model was not really caring that much about what you were telling here, like orange handheld surgical drill, because the surgical drill was always orange and handheld and L-shaped. So what we needed was, even if it didn't look realistic, to provide it with some synthetic data that was different, that forced it to understand what these words, what these descriptions, these attributes actually meant, and respect those. And we achieved that by first sampling a bunch of attributes randomly, surgical drill, T-shaped plastic green, and then using stable diffusion, in this case, the XL variant, to generate these equipment automatically, and then place them into the scene. And you can actually maybe see it doesn't particularly even look realistic. The key point here is we then ask the model to predict this as drill only if the attributes are correctly matching. So this now, over time, forces it to understand, I should pay attention to the color, I should pay attention to the shape, I should pay attention to this, I should pay attention to that. And this was the last key component that was necessary to make this model do what I am about to show you, which is the ability to adapt to novel concepts that it has never seen during training, just by a prompt. The NE stands always for a non-adapted version of this model. So without any additional information, it simply doesn't know what this is. It thinks this suturing done with a much more different looking scissor is close to, whereas with simply a prompt change saying, there is this new predicate called robotic sawing. It's the use of a tool that is white and blue and big and in an irregular shape. And that's also called macro robot. Now it was suddenly able to understand that concept, and the same here by telling, oh, the suture or the scissor, sorry, so far was small and gray and metallic, and now it looks more almost plastic and yellow and big. It again could adapt to that. And the motivation here is not only that people will be typing these, but in the future, the operating rooms are getting more and more digital. And even now, usually you know exactly which tools you are using. So you can automatically input that knowledge down to the serial number of the tool, maybe the CAD model of the tool. You can already use that to automatically understand it correctly. And we also did some quantitative evaluations on this. This is maybe the most boring table. Essentially, the model in general performs better than the previous models and reaches state-of-the-art results. And surprisingly for us, actually Oracle does not even require depth at all. So all the previous methods were requiring depth, which can be costly to acquire, especially with an extrinsic and intrinsic calibration done correctly, and we simply don't need that. And you see that it overperforms for the OR by 5 points. This is a fair evaluation of two non-temporal methods. And if you compare the temporal variant of Oracle to the temporal model of Labrador, then we see a 3% improvement. And already I can tell you 91% is very, very good on this data set. The errors are really minuscule. Sorry, yeah, go ahead.
Yeah, just a quick question. This F1 is for that scene graph prediction.
So the F1, how we are measuring is essentially it's a macro F1 over the predicates that we are classifying.
Okay.
So which means you need to be good in all the predicate types to reach a good result. Otherwise, some occur a lot and are rather easy, like lying on, close to, whereas understanding suturing or cutting is difficult. And this F1 evaluation makes sure that you're really not cheating or you're really good in all of these tasks.
Oh, that makes sense.
And like these results were already great for us, but this was never the point of Oracle. The point was to show some adaptability, some robustness, and this was already very promising result, what we had here. We could, in inference time, give it some views that it has never seen during training. And what I mean by that is 4D-OR always works with 6 views, sees all 6 of them. And if you provide an inference time only one of the views, let's say this one, which is actually one of the better views, its F1 suddenly drops to 50. So from 83 to 50. In our case, our model has seen all possible combinations of these views. So with simply this view, which actually performs very, very well, I think it drops like 1 or 2 points overall to 87, which is a really, really strong performance. What was even more surprising is view 6 is, we didn't even use, this is view 6, by the way, we didn't even use view 6 at all during training of Oracle, whereas it was used for 4D-OR, but you can see 4D-OR, the performance now drops completely to catastrophic levels of 20%, whereas Oracle, it's still not good, but it gets 62% F1, which is really, really surprising for us because it kind of shows the promise that it could potentially generalize to views that you didn't even have during training, to angles you didn't have training. And this is very important if you ever want to build models that can generalize to real-world operating rooms in scale. Kind of along the same lines, we built this adaptability benchmark consisting of 150 digitally altered, but kind of as realistic as possible images of things that were not in the training data set, and then saw that our model without any guidance does not really perform well at all. It reaches an F1 of 31, which is not particularly surprising. Again, this is all things that have not been seen during training, but suddenly with text or visual guidance here, we can improve the 31 to 71 to 78, showing a lot of promise for this idea of keeping the model the same, but adapting it to different operating rooms, different surgeries, simply by changing this guidance, the knowledge guidance. I mentioned that the drill was always orange for us and the sole was always green. And what we wanted to see is what happens if we just digitally change them for inference time. And we see both the previous methods and also our method without any guidance adaptation just simply fail at this task. It's basically 0. Whereas by using visual guidance, so one example saying, this is how the drill looks like now, this is how the saw looks like now, these improve drastically to 75 F1, 79 F1. So there is definitely a lot of potential for these kind of approaches. And finally, the novel predicate adaptation. So what we did is we simply removed a certain type of predicate like drilling or sawing completely from the training set and tested how well our model can understand these concepts in inference time just by a prompt without actually ever having seen them. And this is a concept that's simply not even possible with previous methods. That's why it's not available. And our model with text or visual guidance, it's not perfect, but it reaches around 50 F1, which is, I would say, still interesting because it means essentially roughly every second occurrence of this predicate, it understands correctly. So it's already much better than not understanding it at all. But I think further improvements are needed here. Okay, so I will wrap up kind of a presentation. I think here, because of time reasons, this is as a summary. We mean by holistic or domain modeling using all of this different information we have to understand the operating room as much as possible. And my main focus has always been on external views, multi-view, RGB-D, but in the future, I would actually like to integrate all of these into one model. And I think large vision language models will allow us to integrate multiple of these in one framework. I had some slides, sorry, about applications of SDS. I won't go through them just for time reasons. If you have any questions about certain applications, we can discuss them in that time. So I will stop here to not take too much of your time. Feel free to give me any questions you have.
Thank you so much, Ege. We would like our viewers to audience to give Ege a virtual round of applause. It was a really interesting talk, and please go ahead and ask questions. Any questions? So I had a question regarding the visual prompting past slides that you were showing. So I was just curious that, is there any way you could, like instead of this having so many parameters in your visual prompt, is there any way somebody can go and describe, like while some say, for example, there's like an operation happening and there's another person who's just like kind of having a recorded, like an audio, and that's like that along with the scene, you're kind of feeding that into the model. Have you considered, will that work? Or have you considered, instead of having like a prompt with so many parameters that you keep on changing so as to not overfit? Like it's more like a captioning, like a video captioning, audio, yeah, like an audio file with the captioning, sorry, yeah.
Yeah, no, I think it makes sense. So I think, first of all, I really believe that in the future, we wouldn't be manually modifying these prompts, but the computer at the operating room would automatically adjust these prompts based on what the next surgery will be. It will know it's a partial knee replacement surgery using the strike setup, and it would know how certain things look like in general, at least. So yeah, that's one way. But I think what you mentioned about audio can also be interesting. And I generally like the idea of using as much as possible, like different signals. I think that can also be a promising approach.
Okay. All right. Thank you. Okay. Are there any more questions?
Yeah, I can. I have one more question. First of all, thank you again. It was very informative for someone like me who doesn't know much about OR modeling. But one technical detail I might have missed, that when you say requires depth, like in the evaluation tables, there was requires depth and doesn't require depth. How are you feeding depth into that Oracle model? I thought it was just like 2D patches.
Yeah, it might be confusing. It says does not require depth. It also means does not have depth. So in Oracle, we made this conscious decision of not using depth. Not that it is not possible, but really the motivation was acquiring simple RGB can be done installing one phone, one webcam, whatever. And our depth setup requires you to get certain kinds of sensors like Kinect sensors, then align them across time in a certain way. And then like we didn't think this was a scalable technology that will be easy to adopt at scale on a lot of hospitals, whereas simple RGB recordings are possible. And because the theme of Oracle was how can we build more robust and adaptable, more future-proof models or architectures, we decided to not even include depth in our architecture.
Yeah, that makes much more sense. Another question, like, how do you think this work kind of expanding in future? Because I have no idea about OR modeling, so I'm gonna ask, like, why knee replacement surgeries? Any particular reason? I mean, are they easier or more difficult?
Yeah. Okay, so why knee replacement surgery? Not any particular reason, and almost none of the decisions we are making is based on that. The initial choice was made actually because we knew that we wanted to record a simulated recording, and you cannot record a simulated heart replacement where most interesting stuff happens inside the body. And if you're not going to open up the body, that wouldn't look very interesting. Whereas the surgeons we have talked to said, yeah, I mean, except the fact that there is no blood, your recordings look more or less like how they would look like. And therefore, we decided to go on a more extremity-based surgeries. This was for the reason for the OR. Right now, we actually finished recording a much bigger version of it with Stryker, and there it's also knee replacement simply by the fact that they are interested in knee replacement surgery. So, but I think none of the approaches we have here are limited to knee replacement surgeries or anything like that. Okay,
so in future, like, what would be the next step? Like, if you have to generalize it to another type of surgery, what do you think? Like, what would be the next best candidate?
Okay, so I think if you don't need to record your own data in a simulated way, but actually can work with real data, then the first step I would think of a surgery, again, that can be only solved from external views. And I think if you want to extend this to something like a heart surgery, as I said, what usually happens is the doctors go so close to the patient that any external camera might be occluded. So for anything like this, I would actually consider definitely having an egocentric view as well from the point of the surgeon. Ideally, something on the eyes, but especially like a chest would be fine, head would be fine. I think if you had that input, then almost all surgeries would be possible, but that's something to be considered. Any surgery where external cameras would just be blocked off at the critical phases is not ideal if you want to just solve it from external view. But if you want to include egocentric, then it's also possible.
So basically, you would add more views, like egocentric views, and then if you want to generalize to, let's say, those laparoscopic surgeries that you were showing in the beginning of your talk, maybe those views, if available, because your model is like pretty adaptable to how the number of views it can handle.
Yeah, essentially, like the kind of the sanity check here is, can a human watch the recordings you have made and decide what you are, or kind of determine what you're interested in? Can a human do it? Can a surgeon do it? If not, then obviously you don't have the correct takes. I think it's super interesting to like look into these laparoscopic surgeries, but also consider the external view, kind of both of them at the same time to see, okay, when we go inside the patient, we obviously need and rely more on the laparoscopic view, but not all of the surgeries inside the patient. A lot of happens around the patient. There we need the external view. That would be interesting. And again, for some other settings, some egocentric approaches might be interesting. But I generally, as long as you are ready to collect data or have the data available, I don't think that it is limited to any specific surgery type.
Thank you. Thank you again. It was a very informative discussion.
Since there are not many more questions, and so we would like to close the talk, I would like to request the audience for one more round of applause for thanking our speaker today, Ege. It was a really nice talk and on a very new topic. And yeah, and anybody, if they have any other questions, they can always contact Ege offline. And
exactly, just shoot me an email if you have any additional questions. And thank you so much for having me and organizing this.
Yeah. Good night to you, Ege, and good afternoon.
Thank you.
Yeah, bye. Yeah.
Have a nice day, everyone. Bye-bye.
Bye.
Navisha, if I leave the meeting, your recording will go on, right?
Yes.
Yes, okay.